Hi, everybody. It's Lori Whedon again. I thought we would try the LIRA presentation about misconceptions surrounding climate change one more time. And I figured since we had a lot of technological glitches, I actually ran over, had a lot of questions with other people. I thought maybe I would run through the presentation one more time for you guys so that you could watch this at your leisure. And, any questions you might have, you can share them through email, my email at work, or through Suzanne Gamache, any way that is easy for you. And I'll try to make this pretty quick. It was scheduled to be about an hour and a half. I'm going to try and condense this down to about an hour or less, which means I might be flying through some information, which, of course, if you have questions about anything specific, you just let me know. All right, so without further ado, let's do take two. I am going to be sharing my screen. That's where it all gets complicated. Oh, that's pretty. All right, so I'm going to also be sharing some videos, so I want to make sure you'll be able to hear them all right. I am at home instead of of course, at UMass Lowell, which I'm sure you can tell because of the my background. But what I also can tell you is that I have two cats, and equally sneaky. I have a husband that shows up every once in a while in the background, so um, I can control. The cats I cannot. So if you happen to see anything bouncing around, then you'll understand why. But I'm hoping all you can see right now is the screen. So this picture, obviously taken in Vermont. If you were at the talk, the inside joke here is that I asked my students, can anybody tell me where this happened? And of course, the Vermont is right there in the dead center, so you can figure it out pretty easily. So this is back from July in 2023, where Vermont experienced extreme rainfall, which led to quite a bit of flooding in Montpelier and the surrounding area. So today we're going to be talking about just climate change, misconceptions, mitigation, and moving forward. I probably will not cover a lot of the information you want me to, and I'll do my very best. And of course, then that opens it up for questions that if I can't answer, I can certainly find somebody who can. And so what is my story? Again, this is at the Glacier Bay, watching some nice, speaking of cats, looking at some nice glaciers on a cruise that my mother-in-law paid for, which is wonderful. And it was quite an experience to see glaciers in person, which is something I hadn't done before. This was back in 2018. Going back a little bit further, I went to the University of Texas. I was a Round Rock High School graduate from Round Rock High School, which was, of course, north of Austin, Texas. Went to the University of Texas, started as a biochemistry major, came out 4 years later with a Bachelor of Arts in Art, with painting and drawing being my specialization. I had very little talent, so I needed to get a job, and I started working for American Airlines. So on a dare, I applied to American Airlines. It was the only airline that I didn't need to send in a picture, which I thought was kind of absurd. So started working for American Airlines in 1990, and was going to do it for 2 years, ended up staying there for 20. Retired from American Airlines in 2011. And as I start talking about other dates, you'll realize that I was a flight attendant while I was a full-time faculty member as well. I can tell you in my whole experience, both as a student as a flight attendant and also a lecturer as a flight attendant, I missed a total of 3 classes. So I think I did all right. Um, Continued to fly for American Airlines when I went back to school. Found this place called UMass Lowell. I think maybe you're familiar with it. Came to the Environmental Earth and Atmospheric Sciences department because I wanted to study environmental science, but I liked the foundation in geology that they offered at UMass Lowell, and therefore I stayed there. After graduation, I was offered a free ride for my master's degree at Boston College. At that time, there was no PhD program. My first child was born when I had 1 semester left for my master's, finished up my master, and did not proceed to finish or to apply for a PhD program. So I think it's very important when I'm doing this type of lecture for everybody to understand. I do not hold a PhD. I hold a master's in geology and geophysics from Boston College, where I studied soil carbon sequestration. I feel fairly confident in my ability to explain the sciences, but there is always that tiny bit of doubt people have when I don't hold the credentials that you expect. So I'm upfront, I'm honest. I went to Boston College. I have a master's degree. I do not have a PhD. I was brought into UMass Lowell to teach as an adjunct, mainly because they were desperate and they needed somebody to teach a couple of classes. So knowing that that was an interest I had, I was brought in 2007 and made a full-time lecturer in 2010, and I have remained ever since. I think I'm the luckiest person in the world because I managed to get a teaching position in a university without a PhD, first of all, but also because I love my job. I love what I teach. And I work in the best department in the university as far as I'm concerned. All right. Currently working on a PhD in leadership and education, where my focus is on earth science education in the United States and really the history of it and where we stopped really appreciating the importance of the science. All right, so getting right into the business here. Misconception number one. We are just learning about climate change and its impacts. We need more time to research to make certain that climate change is caused by humans and the impacts will be as extreme as suggested by the scientific community. So we're just learning about it. Surely, we're just learning about it. We need more time. We're moving that goalpost. We need more time. In 1856, Scientific American described Eunice Newton-Foot's temperature experiments with gases and her findings that carbon dioxide caused the greatest warming effects by helping trap heat from escaping the atmosphere. So Eunice Newton-Foot in 1856 actually had done research on carbon dioxide and also water vapor and discovered that they were, as she called them, greenhouse gases. Fun fact, it was the first known publication in a scientific journal by an American woman in the field of physics. So yay, Eunice Newton-Foot. In 1862, John Tyndall expanded on Foot's work by observing the infrared absorbing properties of carbon dioxide and water molecules. Later, in 1895, a Swedish chemist, going back to John Tyndall, is that he recognized that the heat absorbing properties could be directly associated with infrared radiation. So that was his contribution to more clarify Eunice Newton-Foot's work. In 1895, Swedish chemist Svante Arrhenius calculated the potential impact of doubling the atmospheric carbon dioxide level, specifically what it would mean if Earth's temperature. He calculated a 5-degree Celsius increase in global temperature if we were to double the CO2 levels that were what they were back in 1895, which was close to about, I'm going to say, I don't know for sure, but I think it was close to 300 parts per million. This newspaper clipping from August 14th, 1912, in a New Zealand newspaper notes the furnaces of the world are now burning about 2 billion tons of coal a year. When this is burned, uniting with oxygen, it adds about 7 billion tons of carbon dioxide to the atmosphere yearly. This tends to make the air a more effective blanket for the Earth and to raise its temperature. The effect may be considerable in a few centuries. So think about this. This is 100 and, I can do the math, 12 years ago. All right, 112 years ago. So what's very interesting is when I talk about this in my classes where I teach climate change and environmental science to non-science majors, primarily business majors, although I do have some computer science majors that take the class as a natural science. They're always very surprised that we've known about climate change for as long as we have. Most people place it somewhere in the early 2000s or 1980 or something to that effect, but yet we've known about the effect or the potential impacts of climate change for well more than 100 years. So this timeline takes us sort of through really the history of climate science, starting with Fournier back in 1828 or something to this effect, where he started to actually recognize that the atmosphere is responsible for a lot of the warming we see on the Earth. Going back to Eunice Newton-Foot there in 1856, Tyndall, 1862, Arrhenius, 1895, and then, of course, breaking into the 20th century, a couple of the most important things to note are Keeling. So Rolf Keeling began to measure carbon dioxide in the atmosphere at Mauna Loa. away from any impacts of an urban environment. So the measurements of CO2 were a little bit more what he hoped would be uniform. And then, of course, we have the most important ones in my world, James Hansen, and also what's not on here is Carl Sagan. Both went to Congress to speak about the potential impacts of climate change. And this was back in 1985 for Carl Sagan and 1988 for Jim Hansen. And today we're looking at carbon dioxide levels that have surpassed 425 parts per million. When I was born in 1965, the carbon dioxide levels were close to 330 parts per million, and now we're looking at 425. So it's almost increased by 100 parts per million in my lifetime. So that's something really to think about. And when I think about the situation we're in today, I use an analogy that's not necessarily a very pretty one, but it is one that stresses the seriousness of the situation. I think back in 1856, when Eunice Newton-Foote was doing her work, she recognized that carbon dioxide and water vapor were both greenhouse gases. Think of those as carcinogens. By the time we get to Arrhenius, he's recognized the potential impacts and what the lethal dose of those carcinogens would be. When we get to Hansen back in 1988, at that point, it's been identified that we now have stage 1 cancer. The impacts of climate change are now becoming visible. You can actually see the impacts. So we did nothing. And as we continue to conduct business as usual, carbon dioxide levels continue to rise. We find ourselves now here in 2024 with a significant problem. We're reaching levels that will mean we will surpass 1.5 degrees Celsius within the next few years. We're looking at upwards of 4 degrees Celsius by the end of the century. And these increases in temperature, although they may seem small, have an extreme impact on the world. If we wait until we've reached crisis level, we've waited too long. And that's been the hardest part about the communications with climate change, is that the tipping points and the extreme conditions that will occur are bigger than we can change. So what is climate change in general? What are we talking about here? So what did they learn? Well, what we know is that the sun rays go down on the earth and they hit the earth with shortwave radiation in the visible light range. 50% of the incoming solar radiation is reflected back to space, either by bouncing off the surface of the earth, bouncing off clouds, or just the atmosphere itself. The 50% that remains is absorbed at the earth and then re-radiated out as infrared radiation, which is a longer wave radiation. So that's that whole thermodynamics in there. So that infrared radiation we think of as heat. The infrared radiation interacts with atmospheric carbon dioxide and other molecules, and it keeps itself close to the surface, eventually radiating out to space. But the greenhouse effect, as we call it, is actually very important to life on Earth. If we didn't have this greenhouse effect, the natural greenhouse effect, Earth wouldn't be habitable. It would be too cold. It would be close to negative 20 degrees Celsius. And so the greenhouse effect is very important. So having those molecules, naturally occurring molecules in the atmosphere, is a good thing. The problem is when we have too many. So too much of a good thing, of course, can cause problems. The same way taking steroids to replicate what your body naturally produces can mean now all of a sudden you're hitting home runs, right? So in the case of these greenhouse gases, having extra greenhouse gas in the atmosphere isn't a good thing. It accelerates the heating of the planet in a way that isn't necessary. An analogy to that, of course, is Venus, where Venus's atmosphere is 95% carbon dioxide, and their temperature is about 800 degrees Celsius. So its temperature is not a reflection of its proximity to the sun, but the composition of its atmosphere makes it very, very hot. So when infrared radiation interacts with this carbon dioxide molecules, it causes them to bend and vibrate and redirect that radiation back toward the surface. And as a result, we have warming. All right, misconception number 2. The increased temperatures are caused by natural processes in the atmosphere. Humans do not have the capacity to impact the whole world. So there's I guess, a misconception also that we can see the Great Wall of China from space. It turns out you can't. But that's certainly something that's had a significant impact on the whole world, and it's something that's very basic, right? So the idea that we cannot impact the whole globe is a convenient way of dismissing what's really happening. And so let's think about this. The natural way that Earth's climate has changed, and of course, a little bit later, I will talk about that Earth's climate has changed in the past, is through orbital cycles. So we have 3 main cycles that impact the Earth based on physics. We have orbital eccentricity, which is where the orbit of the Earth around the sun goes from more circular to more oval. That's about a 100,000-year cycle. And it's the one that's been the most impact to the glacial and interglacial cycles over the last 400,000 years. Earth also has a tilt. Its tilt goes between about 22 and about 24.5 degrees. And that impacts the severity of the seasons. If the Earth had no tilt, if its axis were perpendicular to its orbit around the sun, we'd have no seasons. It would be simply spring and autumn all the time, which would be fine for us here in New England, but would make most of the Earth uninhabitable. So we have a tilt, and the tilt itself actually wobbles. And so not only does it vary between 22 and 24.5, but it actually wobbles on its axis, and we call that the axial precession. So today, the Earth's axis, when we look about where is north, it points towards the North Star. About 12,000 years ago, it pointed towards the star Vega. That was its North Star. And so the Earth's orbit, as its tilting is changing and as its eccentricity is changing, it's actually wobbling on its axis. And that also impacts what the seasons are when the Earth is closest to the sun and furthest away from the sun. So today the Earth is closest to the sun in January, furthest away from the sun in July, and that is fine and dandy for us in the Northern Hemisphere. The Southern Hemisphere is not impacted quite as much because it's primarily water, and water has a real moderating effect when it comes to temperatures. All right. So is it volcanoes? It turns out human activities emit 60 times the amount of carbon dioxide as volcanoes each year. And I think this is important. And again, we'll be talking a little bit about volcanoes later, is that volcanoes do emit CO2 and water vapor and many other things. But the impact as far as the total carbon dioxide levels that are released, it is minimal. And one of the questions I got in class also when I was doing this was, how about the increase in human population? How has that impacted carbon dioxide levels? And it is a minuscule amount. Again, I do have my students calculate that out, but it is a very small amount of increase. All right. So when I show you this is a graph that explains all the potential forcers as far as that could impact Earth's temperature. And it goes from aerosols, land cover, ozone, all human drivers. And I'm going to include volcanoes in here too, just so you know. So when you look at the changes in temperature that we've seen here on globally, if you consider all the natural things such as volcanoes and just the variability of the sun, goes the sunspot cycles about once every 11 years. Has that had an impact? Has the sun gotten stronger? All of these things. What you'll find is that those natural causes are very minimal. All human drivers include ozone, which is increasing in the troposphere, which is the area of the land of the atmosphere where we live. And having it in the troposphere is not good. And it's a byproduct of we call photo pollution. So that means that the sunlight hits these nitrogen oxides that are coming out of tailpipes, and they create ozone, which is an exothermic reaction, which means it releases heat. Land cover change, cutting down trees actually has a slight cooling effect because the bare surface is more reflective than forested area. Although forested areas are very good because they remove carbon dioxide. But in this case, we're just talking about temperature changes and not CO2 changes. And then aerosols can actually also have a reflective effect. Aerosols, byproducts of industry and so forth that go into the atmosphere that are small particles that can be reflective and actually having, again, a slight cooling effect. If you also look at the greenhouse gases, which we have here as a purple line here. So this purple line is greenhouse gases, and that if we didn't have all these other drivers, the temperature increases would be more like this. But the red line that we're seeing right here, that's all human drivers, and it also happens to follow the line of observed temperature changes. And so that's really why we look at this is what is it? Is it natural causes or is it something else? So let me go over really quickly to this web page so you can, I think this is when everything started to go wrong. I tried to skip around to a web page just to see this graph in action. Okay, so this is a graph that includes all of the observed temperatures globally, and that's what all these dots are. That's the temperatures that we're seeing, right? And then natural and human caused. And so the one I'd like to point out here, of course, is volcanoes. And so volcanoes, Mount Pinatubo erupted around this time, which had shot a lot of ash into the atmosphere, which is, again, very reflective as an aerosol, and it actually had a cooling effect. So we can see changes. They're very sensitive changes to Earth's temperature on, considering all of these natural and human-caused changes, so they can impact the Earth's temperature. Here's my land use change. There's my aerosols. What else do we have here? We have solar radiation output. Again, that's really not impacting the temperature at all. Here's our ozone. And then, of course, here is our greenhouse gases. And then this is all factors combined, which align very nicely with what we're seeing observed. So, all right, going back here. All right. So again, I love this quote, but I can't read it right now because I can't see it. All right, so hold on a second. Let me move this if I can. All right. So this is from All the Light We Cannot See by Anthony Doerr, which was a wonderful book, also made into a mini series on Netflix. I love it. I thought it was incredibly well done. I love the book. So I'm going to read this to you. It's a quote, and I think if you guys have read the book, you know that the kids listen to the professor. It's one of the things that brings them joy is they get to hear things in their little headphones. And this is the professor talking to the children. Consider a single piece glowing in your family stove. Do you see it, children? That chunk of coal was once a green plant, a fern, or a reed that lived 1 million years ago, or maybe 2 million, or maybe 100 million. Can you imagine 100 million years? Every summer for the whole life of that plant, its leaves got caught what light they could and transformed the sun's energy into itself, into bark, twigs, and stems. Because plants eat light in much the way we eat food. But then the plant died and fell probably into water and decayed into peat. And the peat was folded inside the earth for years upon years, eons in which something like a month or a decade or even your whole life was just a puff of air, a snap of two fingers. And eventually the peat dried and became like stone, and someone dug it up, and the coal man brought it into your house, and maybe you yourself carried it to the stove. And now that sunlight 100 million years old, is heating your home. What I love about this, first of all, hey, geology in a book. I love it. But what I love about this is that it really brings to life in a way that literature and art communicates the intensity of what we're looking at in a way that science can't. And if you can imagine sunlight 100 million years old, it's more like 300 million, but we'll get into that later. If you have this released all at once, as we do when we burn coal, we're releasing and burning forests all at once, that it's been stored, that light's been stored all these many years. If that's easier for your mind to visualize as opposed to these, I don't know, nebulous little molecules that go into the atmosphere that hold on to heat, then think about that. When we burn coal, we're burning entire forests that have been buried for millions of years and releasing all of that light. And of course, we think of that light as heat. And that's what the whole impact is of this climate change business. But let's talk again about, here we go, coal. So how does coal form? It turns out that most of the coal comes from this Carboniferous period, which was about 300 million years ago. At this time, forests had developed the woody parts to them, like this material called lignin. But bacteria and other decomposers had not developed yet. They haven't evolved. So all of this woody material kept building up year after year after year. They'd get buried and, you know, water would cover them and then more sediment would cover them. And over years, the compaction and the pressure and the heat changed them from what we think of as peat to coal. And so again, we're talking material that is as vast as a forest that's compacted and compacted and compacted into a very small material, a little coal seam. So that bit of coal really does, when you're talking about burning coal, you really are burning a really old forest. All right. So is population the problem? And so you can look at this graph and you know, it shouldn't be too surprising to see that, I'm trying to move this here again. Oh my goodness. Okay, I can't. So it's pretty easy to see that the world population and anthropogenic carbon dioxide emissions run parallel to each other. It's pretty telling, and it shouldn't be terribly surprising. So every person, regardless of where you are, has to eat. Every person has some form of shelter. Every person has to be clothed. And all of these impact your use of resources. If you are cold, you have to be warm. And the way to be warm is to usually build a fire. Every person has an impact. Every person has a carbon footprint. And as population has skyrocketed, starting with the baby boomers in the early to late 40s, we're looking at a parallel increase in carbon dioxide emissions, methane emissions, habitat loss, biodiversity loss. All of these things go along with that increase in world population. Tough subject. We're now looking at, we have 8 billion people in the world. This graph only goes to 2000, looks like maybe 2010. We reached 8 billion in last year. I think it was last year. And when I was born in 1965, population was 3.1 billion. So in that time, in that short period of time, we've increased the number of people by that much, which is pretty striking. All right. So I'll eventually figure out how to make the thing move. Okay, there we go. All right. So going back to how we measure carbon dioxide levels, another interesting thing is when Ralph Keeling started examining or measuring carbon dioxide levels at Mauna Loa, he noticed it had sort of a zigzag pattern to it. So it has a seasonal variability. And so today, the carbon dioxide levels are a little more than 425 parts per million. When I was born in 65, they were 3.3 parts per million, which sort of throw that out there. But here's the other thing. The variability is because most of the land mass in the world on Earth is in the Northern Hemisphere. And in our spring and summer, leaves pop out, the sun is higher in the sky, and photosynthesis rapidly removes a lot of carbon dioxide. And when that happens, carbon dioxide levels actually briefly fall. So right now they're 425, but if you examine or you check out the carbon dioxide levels in August, they're likely to be much lower than that. Say they'll be about 420. So they'll vary between those two basically seasonally. And then, of course, when the leaves fall off and the sun is further in the horizon, what happens is those CO2 levels come up again. And so we have this zigzag pattern to them, but the overall trend is upward. And of course, looking at this, this shows you how in the northern hemisphere, which of course is on the right in this graph, that shows us where the majority of that landmass is. The southern hemisphere, we have Antarctica, we have Australia, right? Little bits of South America, but we don't really have as much land mass. And so that's the reason why there's not that evening out with the southern hemisphere's answer. When we're in our winter, they're in their summer, but it's just not the same impact. So that's why we see the zigzag pattern. And of course, we can look at ice cores over many, many years, up to 400,000 years ago, maybe even more at this point, where we can examine carbon dioxide levels. And the cool thing about that, we can examine carbon dioxide levels. We can also look at isotopic evidence and really figure out what the temperature was way back then too. And so the carbon dioxide, we're able to get little snapshots of what the Earth's atmosphere was like at the time the snow fell that eventually turned into that glacial ice. And we can do that because each little sliver or each little bit of glacial ice carries in it has all these bubbles. And those bubbles are little tiny pockets of atmosphere that are the representative atmosphere when that snow fell. It's really amazing. If you think about a snowflake, it's a fairly porous six-sided figure, and it compacts and it compacts, and as it compacts, those little spaces in between the little ice crystals actually hold in place that little bit of atmosphere. And we're able to actually examine that and determine what the levels were at the time. All right, misconception number 3. James Inhofe brought a snowball to the Senate floor in February 2015, thereby providing evidence that climate change is a hoax. More recently, Congressman Doug LaMalfa compared climate change to seasons. He was in Congress speaking to Pete Buttigieg and said, "I got your climate change, it's called the seasons," in which case Secretary Buttigieg looked at him very confused, as if he must have misunderstood. So climate change denialism is still happening, even in 2024. It's becoming more bizarre, but it is still there. And here's James Inhofe here in February in Washington, D.C., presenting said snowball. I got nothing except for to say weather and climate are not the same. The first thing I can say, weather, when we talk about the weather, we're talking about the atmospheric conditions at a specific place at a specific time. What is the cloud cover? What is the temperature? What is the wind? Atmospheric pressure? Is it raining? Is it snowing? What's happening? That's the weather. The climate is an average of these atmospheric conditions over a long period of time. A way to think about this is if you're going on a trip to Arizona in July, would you look at the weather or would you look at the climate? Now, you might assume the climate's going to be hot, super hot, and all you're going to need is sunscreen. When in fact, the rainy season that occurs in Arizona occurs in the month of July and August. And so climate is not helpful. Climate is an aggregate of averages, atmospheric conditions in an area. Weather is what's happening outside right now. So if you can understand the difference between those two, you can also correct somebody who says, hey, it's 70 degrees and it's January. This must be climate change. You say, that's weather. Now, here's where it gets annoying for the general public. If the whole month of January is 70 degrees, now we've got something. In this case, we can say that the probability of a whole month of January being 70 degrees without the impacts of anthropogenic climate change is very low, meaning that the probability that climate change has caused the month of January to be 70 degrees in Lowell, Massachusetts, that's something we can say. The general public likes absolutes. Can you tell me this is because of climate change or is it not? But science and the scientific community doesn't work in absolutes. We work in statistics and probabilities. And so one weather event of a snowfall in February, I guarantee there's no way to connect that to climate change. The flooding that was experienced in Vermont and the amount of rainfall that happened in one day, you can say that the probability of that happening without climate change is low, but it's never zero. All right. I hope that made sense. All right. And again, anytime I can show the Simpsons. So climate and weather are not the same. So we know that. All right. So the other thing that can happen is just because we have climate change, that doesn't mean we're not also going to see extreme cold temperatures. Ask anybody in Texas. I'm sure they spend a lot of time telling you about it. So what happens with climate change, and this is another thing to look at very carefully, is the 1951 to 1980 is the average that we use as a comparative. So we're looking at the average temperatures between 1951 and 1980. And if you looked at that time period, you'd notice that the temperatures fall on a normal distribution pattern. And you have extreme cold, you have extreme warm. But with anthropogenic climate change, and certainly over the last couple of decades, the shift has happened so that we have far more extreme hot days than we do cold days. And that's something that is kind of lost. The other thing is that the kurtosis of the normal distribution has changed as well. So we don't see it as quite as peaked. It's more of a spread out where we still see some of those cold days, but we see far more warm days. So putting at this in sort of a visualization. So you think about it in 2022, in the United States, there were 50% more high temperature records that were broken than low temperature records. I'm still waiting on the information for 2023, but I expect it to be much higher than 50%. 2023 was the hottest year on record. And so how could we get cold days when we have climate change? And so this is very recent research. Again, I try very hard to stay up on some of the science. And so what happens is what we're looking at right now is the Arctic happens to be warming much faster than the rest of the globe. It has a lot to do with melting ice and so forth, which I'll get into a little bit later. But when you have a warmer Arctic, that means that your temperature differences between the far north and the areas below, it's not as, the contrast isn't quite as great. When you have that, it impacts the jet stream. Now, I'm not sure if you're familiar with the jet stream, but it's a very fast moving, moving air in the atmosphere at about 500 millibars. So up, where airplanes fly. If you were flying from Boston to Los Angeles, it usually takes longer to get to Los Angeles than it takes to get home, simply because the jet stream impacts you're going against the jet stream, it takes longer, or you have to go around it. And if you're going with the jet stream, it allows you to move a little bit faster. So that's really, when you think of the jet stream, that's what you can think of. But when the jet stream weakens, more importantly, the jet stream happens to kind of act as sort of a barrier between the cold and the warm air. And when the jet stream weakens, it develops more of those waves. We call those Rossby waves, and those waves develop. And when those waves develop, the boundary now between the cold and warm has reached further south, if we're talking specifically about the Northern Hemisphere. And so it reaches further south, bringing with it that cold air. And so the best example here is this image right here, where we look at the wavy jet stream and the cold air that makes its way into the center of the United States. The warm air could be right here. There was a time when it was very, very cold in Texas. This was a few years ago when they had their really serious cold snap, but yet it was in the 60s in Alaska. And of course, Alaska also has that panhandle, and that's where they saw most of that warmth. So again, it's something to really think about. All right. All right. Misconception number 4, even if climate change is real, it won't impact me or my children or my grandchildren. It's centuries away from making any impact. All right, a little experiment you can do. In fact, you can do this with your kids or your grandkids or your great-grandkids or neighborhood kids or who knows what. You take 2 bottles of water, you put some stones or whatever on the bottom, and you make sure that's to make sure they don't kind of fall over. You fill them about halfway with water. In one, and I chose this little one with the red top here. In one, you're going to put Alka-Seltzer. Now, Alka-Seltzer releases carbon dioxide. Carbon dioxide's heavier than air, so it remains in the bottle while the rest of the air sort of goes out. And then you put in some little thermometers. You put them outside in a sunny day, and you wait a little bit, and eventually the one with the carbon dioxide gets warmer than the one without the carbon dioxide. And so this was only after 30 minutes. And it was really interesting is because Alka-Seltzer, that reaction is normally, it's initially an endothermic reaction. So it means it initially gets colder before it gets warmer. So this is after 30 minutes when the initial one was actually much colder. I think it got down to about 3 degrees cooler than the other one and then shot back up. So if it was a super sunny day, if I were somewhere like Texas, I would leave them out for longer. But it's just an example of simple science that you can do in your own backyard to really show you the greenhouse effect. When you look at this image, what it's showing is all of the different countries on the globe. It's comparing it to that 1951 to 1980 average temperature. Where it's blue, it's below that average. Where it's yellow, orange, or red, it's above that average. And so this only takes us up to 2017, but it allows you to really see how there is a sort of a trend towards much warmer. And certainly by the end of that, you can see that. Another way to look at this is we can examine, again, if you see this, there's a green line, which you can barely see. That's that average, that 0 degrees right there. And so as that green line, we start seeing that as the century progresses, we start seeing temperatures get warmer and warmer and warmer compared to that average. There is one anomaly there when we see this. In 1940s, there was an El Nino event that was relatively strong, and that caused some warming. So when you see that, you saw that little warmth thing, that was attributed to that. Some people in the past have been saying, oh, that was World War II. That must have had something to do with World War II. Well, it's more of an El Nino than it had anything to do with World War II. And so this takes us up to 2022. And the cool thing about this is it allows us to see it in a different way. Again, art and visualization, these things are so much more useful as far as communicating these things than any science could be. But here's that 1940s anomaly where it got very warm because of an El Nino, but it got relatively cool quickly because of a La Nina that followed it shortly thereafter. But kind of avoiding or not looking at that one, but starting to look at the overall impact. I mean, it's pretty obvious. It's getting warmer and warmer and warmer. 2023 was, again, the hottest year on record. So if you look at this graph, the orange line is the temperature. The dashed line is about an average between 1979 and 2000. So we're even moving it further up. This solid black line right here is 2024. So we were headed for an even warmer year in 2024. We're still in an El Nino. We'll probably transition over to a La Nina later on, but right now we're still looking at very warm temperatures. Satellite data. So remember, our misconception here is it's not impacting me today. All right. So here's satellite data about sea level rise. Now, sea level rises for two reasons. You take land-based ice or glaciers and you add them to the water, thereby increasing the volume. And there's also what we call thermal expansion. So thermal expansion is actually the fact that warmer water just takes up more space. And so as it gets warmer, it expands. And that could be responsible for up to 50% of the sea level rise that we see. We recognize sea level rise on days like this, which is in Miami, where there was a clear day flooding event. And this clear day flooding event is what happens when you have a high tide and a time when the moon and the sun are in alignment, or what we call a spring tide. Sometimes that high tide can correspond to what we call the perigee, where the moon is closest to the earth. And when that happens, it's even more extreme. And we call those king tides. And so king tides are becoming more common and they're becoming more extreme. So we actually see king tides that water level rivals that of hurricane storm surges. Now, hurricane storm surges tend to be a little bit more violent, but here, look at this king tide in 2017 and in 2015 was greater than Isaac and Faye hurricanes and Mitch. All of these were pretty extreme hurricanes, but yet the king tides were actually greater as far as that's concerned. So that's really wild. And if the Florida doesn't mean much to you, how about Boston? So Morrissey Boulevard has been having problems also, excuse me, Morrissey Boulevard, but also your areas by the piers, by the aquarium, they've all been underwater this year a couple times, and that is directly related to high tide flood days. Those days will continue to increase. They are expected to increase quite a bit. So if you look at this map right here of Boston, as years progress, the days per year that we have clear day flooding or high tide flooding is going to increase dramatically. All right. Extreme rainfall. Now, this is something that it's always tough to count on eyewitness testimony. All right. In fact, eyewitness testimony tends to be one of the most fallible ways to identify a suspect. I know this because I also teach forensic geology, which is a lot of fun. So our eyewitness testimony, for myself, for example, I think it just seems like the rain is always just really heavy rain. There's no more of that gentle rainfall. Am I losing my mind? Is that really the case? Data suggest that it is. And so this is not unexpected with climate change, but we're actually starting to see an increase of the amount of extreme rainfall. Warmer air can hold more water. And when warmer air holds more water, we see heavier rain events. Going back to that time in Vermont when it was raining really, really hard, they had a month's worth of rain in a day. The same thing was going on in Greece and in Libya, where they had extreme, extreme rainfall. In the case in Greece, we're talking half a year's worth of rain in a couple of days. And so when we look at that, that alone tells us something pretty special about the things that are happening. We're starting to see more extreme rain. And so where we're seeing a lot of rainfall and extreme rain, they're seeing extreme drought here in the Southwest, which is only going to get worse with climate change, which is a problem because we grow a lot of our food in California, and that relies heavily on the Colorado River. Sea surface temperatures. Now, this one's pretty crazy. So this is a key in the Keys here of Florida. Temperatures reached 101 degrees. And so I won't take the time to show you this video, but what I can tell you is that the, well, let's show you, because I don't want to tell you anything incorrect. All right, we're waiting ever so patiently for this to show up. Okay. This is old, good old Weather Channel. There we go. You should be able to hear this, hopefully.
Maintaining your sweep.
The ad. highest we can read. %22% were reported alive. That's very sad. I don't know how many of you have ever been to Florida, but some of the water is beautiful. It's always, warm, but not hot. It's also very hot and humid in Florida, and I'm going to go with the last thing I would want to do is get into a hot tub when it's when it's that hot outside. But the point is that coral themselves are stressed for many different reasons, but one of the biggest is heat. And coral themselves have a symbiotic relationship with these zooxanthellae algae, which provide food, and then the coral provide them with shelter. When they get too hot, they start producing toxins, so the coral have to expel the algae, and that leaves them bleached, or that leaves all the color gone. And where it becomes a bit of an issue is that if that zooxanthellae does not return to the coral within about a month, the coral starves. And it can get some of its own food, but not enough to survive. And so that's why we see these massive die-offs, not just here in Florida, but also in the Keys. All right, in the Great Barrier Reef. So, all right, number 5, even if climate change is real, a few degrees really doesn't make a difference. That's one of my favorites. All right, so let's talk about a few degrees. The Arctic, as I said earlier, is seeing more warming than anywhere else on the Earth. If on average we're seeing a temperature change of about 1.2 degrees, I guarantee that at the Arctic, they're seeing more like 4 degrees. So they've seen a huge, huge change in temperature. And of course, I'm talking Celsius here. And part of the reason for that is a positive feedback loop that is pretty efficient. So as the Earth warms, ice begins to melt. Now, ice is very reflective. You go outside on a snowy day, the first thing you do is, you got to put some sunglasses on because it's so bright, because that snow is reflecting all the sunlight back to you. When the snow and ice melt, there's less of that and more, especially if you're talking about the Arctic, where there's snow, and then beneath the ice, and beneath the ice is the ocean. Well, the ocean absorbs water very well. The ocean absorbs sunlight and heat very well. And so as more ice melts, it exposes more ocean, which absorbs more heat, which melts more ice, which exposes more ocean, which absorbs more heat. You see where we're going with this. And so it creates a cycle of destruction, essentially, where you end up with very little ice left. So I will show you this video if I can. And it is all right, I know they're speaking on this, so let me make sure that you can see it.
Education for all? We're all in. All over the country, instructors are improving student success and retention rates by...
If you can hear this.
In 1978, satellites began continuously observing the polar regions, and the dynamic beauty of the Arctic sea ice was revealed. What we expect to be a solid mass of ice is actually in constant motion. As researchers continue to seek a deeper understanding of this region, new information about how sea ice changes is coming to light.
In this animation, we're taking Arctic sea ice into the 3rd dimension. Here, we're looking at the ice age, which is an indicator of thickness. Generally, older ice is thicker ice.
That's the voice of Dr. Walt Meyer, Senior Research Scientist at the National Snow and Ice Data Center.
What you see in this animation is the ice pulsing out and in with the seasons. In winter, the ice grows out and expands outward. In summer, it contracts inward as it melts. You see the whiter ice, which is the older ice, moving around the Arctic, being pushed around by winds and currents that move the ice. Over the years, the ice pulses around and moves around towards the top along the coast of Greenland. The older ice eventually moves out of the Arctic and into the North Atlantic, where it melts. The ice gets replenished within the Arctic because some of the ice survives each summer and grows older, and particularly in a region north of Alaska called the Beaufort Sea, where the ice spins around in a clockwise direction called the Beaufort Gyre. And that ice can keep spinning around, oftentimes for several years, and gradually getting older and thus getting thicker. Eventually, the ice will spin out of that gyre and go out through Fram Strait. In the past, we've always had enough ice growth and ice aging, enough ice surviving the summers to replenish the older ice that's lost. But in recent years, we've seen less replenishment. There's been more melt during the summer, so the ice that goes out through Fram Strait has not been compensated by the ice growth. In addition, especially in recent years, we've seen some pretty remarkable things in the Beaufort Sea, where that area that used to be a nursery for the development of the older ice allowed the young ice to age and mature. What we've seen instead is the ice is now more broken up, more scattered, and that's allowing the older ice to melt within the Beaufort Sea. So we're seeing the Beaufort Sea go from a nursery to a graveyard for older ice. As we get towards the more recent years, much of that oldest ice, the ice that's older than 5 years old and the bright white, has almost virtually disappeared from the Arctic Ocean. And the Arctic is now dominated by younger and thinner ice.
Yeah, that's pretty extreme, I guess you could say. And I mean, that's important for you to be able to really kind of get a full idea of how much of this sea ice is gone. Sea ice itself, it's exposing the Arctic Ocean, which will cause more complications in weather and certainly forecasting, because we now have a whole new source of moisture that wasn't there before. And how is that going to impact the Gulf Stream and so forth? I mean, all of this would be a very exciting time to get into meteorology, but it's going to be complicated, and it's going to be very interesting to see how this works if one could be completely objective. So glacial mass, and this is, of course, in Europe relative to 1997. So we're talking about the Alps in this case. A lot of work has also been done to look at glaciers in the Andes, and also, of course, in the United States. Glacial National Park will soon be without glaciers within the next probably a couple of decades, because where there's so much glacial retreat in that area as well. And certainly in Alaska, we see glacial retreat too. And also in Greenland and Antarctica, we also see glacial melt. So Antarctica, West Antarctic ice sheet is melting more than the East Antarctic ice sheet. And of course, this image is old, but it does show the relative difference between West and East. However, we are starting to see some loss also in the East Antarctic, and there's some that we have great concerns about over in the East as well. So what happens is that when you have ice that's already in the water, it's already displaced the amount of water that it would become when it melts. But the problem is that the ice shelf is actually kind of like a cork holding back the ice that's on land. And as it melts, and once it melts and it's below what we call the grounding line, that allows even more warm water to interact with the ice, which will then really accelerate the melting and the calving of land-based glaciers into the ocean, which would, of course, be pretty catastrophic as far as sea level rise is concerned. So again, we can see that there is a significant decline in ice in both Greenland, which is the blue, and Antarctica, which is the red and pink. This is Mendenhall Glacier, which I visited back in 2018, and a beautiful, beautiful place there in Juneau. But this glacier itself, we used to be closer to where this tree is. I can show you in a time lapse. If I can get to Juneau, I think I'm going to have a little trouble finding this. So let me go down to, actually, I'll let you see this one. It's not the same glacier, but it kind of shows you the retreat of glaciers over time. So this is a glacier that's retreating. This is Columbia Glacier in Alaska, and it's accelerating more so in the last couple of decades. It's always important if you're looking at glaciers to make sure that you're looking at them in the same time of year, also because glaciers retreat in advance seasonally, but if the overall trend is retreat, then it becomes relatively significant. And this amount of ice being lost over this time period is not something that is seasonal. This is something that is a significant decrease in the amount of glacial ice that we see. This, by the way, if you ever want to just waste some time, go to the Google time lapse. You'll just sit there and forever just watch all sorts of different things. So that was supposed to be our coffee break. It's over. Because I want to get through this. All right, misconception number 6. The climate has changed before, so what's the big deal? Now, this is one of the things that is an interesting way to look at it. You're absolutely right. The climate has changed before. The Earth used to be a snowball in space, right? It varied between a snowball and a hothouse. We're talking, 700 million years ago. The Earth has experienced since the Cambrian, and Cambrian, which is when we start seeing an abundance of multicellular life. Not that it didn't exist before then, but this is what we see in the fossil record. There were times when there were exceptionally high extinction rates. In fact, a lot of the geologic periods are noted by extinction events. So at the end of the Ordovician, we see a fairly significant extinction event. At the end of the Devonian is another one. This is the end of the Permian, which I'll get to in a minute. And then we also have one at the end of the Triassic. And the one that most people are familiar with, of course, is the one at the end of the Cretaceous. Now, this is looking at animal families, and this is marine life specifically. So I'm going to go back to this guy right here. So the end of the Permian extinction. The Permian extinction was kind of an interesting time period because this is a time when Pangea had formed, and Pangea took, the several different continents and combined them all to one supercontinent, which greatly decreased the available coastal area. And a lot of marine life evolved around coasts. That's where there was an abundance of sediment that brought nutrients that allowed for, the type of bottom of the food chain that one would hope to have. And what was really interesting is that was already a stressor that was on marine life at that time. But another thing that was happening is in what's now Siberia, there about over 500,000 years, there was an abundance of volcanic fissure eruptions. So this is what we call massive amounts of lava just outpouring year after year after year after year. And in that, as I mentioned earlier, that volcanoes do release some carbon dioxide. Over that 500,000 year period, carbon dioxide levels actually increased sixfold. So we had, 6 times greater than what it was when prior to the eruption of those Siberian traps. And that carbon dioxide levels, they really went up, we'll say over 100,000 years. The increase in carbon dioxide, the rate at which we are adding carbon dioxide to the atmosphere today is close to 100 times faster than what caused the greatest extinction event in Earth history, where 95% of marine species and 75% of land-based species went extinct. Let that settle in. We're increasing carbon dioxide levels close to 100 times faster than what happened at the end of the Permian that was the greatest extinction event in Earth's history. We're adding it at a rate that has never been seen before. That's the scary part. It's not that climate's changing, and yes, it has changed before. It's the rate of change that is so terrifying. The other thing that comes along with this, and this is one of the things that is most disconcerting, you could say, is the idea that should we not act on climate change, we will reach a point where we have surpassed a tipping point. And there are a few of them. Some of the tipping points are already we're starting to see evidence of, such as permafrost melting and releasing methane, which only accelerates the amount of carbon dioxide in the atmosphere or greenhouse gases in the atmosphere. Arctic sea ice disappearing is something else that we're seeing. We're starting to see an impact to our thermohaline circulation, which is this wonderful conveyor belt that distributes warm waters further north and bringing down cooler waters to be rewarmed, kind of like your veins and arteries. That's starting to be impacted because of the melting of the Greenland ice sheet. The coral reefs in Australia are already starting to see die-offs, massive die-offs because of bleaching. The Amazon rainforest, if we see upwards of 25% of the rainforest deforested, we're now going to, the Amazon will then transition to be a carbon source instead of a carbon sink. Right now, it absorbs more carbon than it releases. But if there's enough deforestation in that area and you expose enough of the soil and you continue to do agriculture in there, you're changing the land use, you're going to change the whole hydrologic cycle in that region, and it's starting to become a source of carbon instead of a sink. When these happen, these are not easily fixed. And so these tipping points that we're talking about, it's very difficult to imagine reversing direction at that point. Certainly thermohaline circulation, there's nothing, no technology that we have, nor would we have in the next 1,000 years that would be able to help thermohaline circulation get back in line. If it collapses, it would be devastating to food production, to life in Western Europe, and it would just be catastrophic to extreme weather events as well. So these are things that we're trying to avoid. And when we say that we're going to surpass some of these tipping points, we're already looking at something that we can't fix. Should we wait longer to address climate change, it's going to get even more severe. These are methane cath rates. Now, methane cath rates are a very special tipping point that we really do not want to pass. Methane cath rates are these think of them as cages of ice that enclose methane within them. And simply because at the bottom of the ocean, there's organic material, there's methane, and it gets sort of trapped in ice. You bring them to the surface, you can set them on fire because they have methane in them. When the ocean water becomes too warm, they become unstable and they will rise to the surface and release that methane, which would be, again, not good. This, of course, is what's happening in the Arctic areas. This particular one is in Alaska, and I'll show you a video here in a second, where you have the melting the permafrost, you have trees and other things that are falling into lakes, you have sediment that's being disturbed, that's releasing methane, and that those methane bubbles become trapped in ice. And so this is always a winning a winning little video here. All right. So I will play this. Wait. Okay, I see what's happening here. Oh dear.
So
you got to watch a commercial first.
Wow.
I love it when that happens.
Grads could get a $500 rebate over and above most other offers. Toyota, let's go places.
We're out standing on a frozen lake in interior Alaska, outside of the University of Alaska Fairbanks campus. And this ice is already about 20 centimeters thick. So as it's been freezing up, methane gas has been coming out of the bottom of the lake and getting trapped in the lake ice. If you look at the shore, you can see that there are lots of trees that are falling in the lake and they're dying. What's happening is the permafrost is thawing. The ice that was in the ground, when it melts, causes the ground surface to collapse. When the forest falls in and any organic matter, dead plant and animal remains that were in the permafrost, thaw out in the bottom of the lake, microbes decompose it and it generates methane. And methane doesn't like to stay in water in solution. It forms bubbles, and those bubbles make their way to the surface. In the summertime, the bubbles pop and they enter the atmosphere. In the winter, however, this ice forms a cover on the surface of the lake, and the bubbles get trapped right under the ice, and then the ice thickens and freezes around them. And so what we have out here is like a time-lapse photograph of methane emissions from the lakes. Methane is a very potent greenhouse gas. A molecule of methane is 25 times stronger than carbon dioxide. Methane is formed in millions of lakes around the Arctic where permafrost is thawing. And each year, these lakes are emitting already tremendous amounts of methane. But when we look at how much carbon is in permafrost still frozen, and the potential for that permafrost to thaw in the future, we estimate that more than 10 times the amount of methane that's right now in the atmosphere will come out of these lakes.
So that's fun to watch, but horrifying when you realize the reason for it. So another problem that is going to impact us, should we continue with business as usual, and we're looking at a 5 degrees Celsius increase in temperature by the end of the century, we'll be expanding the habitat area for disease-carrying mosquitoes. And so this is the areas of red will be, there's where we are currently. You have 12 months out of the year disease carrying mosquitoes that are found. As we continue to heat the planet, we start seeing more and more like an encroachment of at least 1 or 2 months out of the year where we start seeing these mosquitoes that can thrive in these environments. And these are mosquitoes that carry yellow fever, malaria. They carry West Nile and Eastern equine encephalitis. All of these are very impactful to humans, but also think about the impact for pets. Right now, the impact of ticks and so forth that are also becoming more prevalent don't just impact humans, but they, of course, also impact your pets. So it's one of those things. All right. So the most of this has been pretty overwhelming and kind of depressing. And what can we do? So this is always sort of going back to that whole idea of how we have stage 4 cancer, if you will. I look at the situation with climate change, and I look at everything we have to do. And then I look at the United States today. I look at the Inflation Reduction Act, which was the biggest effort to address climate change that's ever happened in this country. And yet I realize it's so far from what needs to be done. I look at money that's used to send people to space, which is good for you. But that same money could be used to address these issues on the planet we have right now. I think about all of the challenges we have ahead of us and what would happen if we do nothing. I admit to you that I am a geologist and I'm an educator. I am not an economist. We have an economist at UMass Lowell who teaches climate change economics, and I would love to sit in our class. But what we have to do is so extreme and so groundbreaking. We need everyone to act. So what can we do? We can do two things. We can adapt, which means, oh, it's going to happen, so we might as well figure it out. Or we can mitigate. Think of adaptation as addressing the symptoms, but mitigation is addressing the disease. And so adaptation is things, we already have to do this, right? So Boston is already flooding. So we're going to have to figure out a way to prevent Boston from flooding. Mitigation means stop using fossil fuels, change the way we produce energy so that we can avoid some of the catastrophic effects that are going to be happening. Start figuring out a way to capture and sequester carbon. Be more energy efficient. You know, stop eating beef every day. You don't have to stop eating beef completely. You really love it, but try and get grass-fed beef. You know, the concentrated animal feeding operations, or CFOs, they are so horrible for the environment, so horrible for climate change, and so horrible for the animals. But yet they're so cheap, and that's why we have so much red meat in this country, which is bad for your health. Adaptation, conserve water. Water coming out of your faucet is not free. It took energy to clean the water. It took energy to get the water through your pipes. All of these things, these little steps you can take, are useful. You should also understand that people, basic people in what you do in your world, are not responsible for the majority of what we see. Industry and energy generation is a biggie. But what we can do is be smarter about the way we eat food. We can be better about food waste. We can be better about many things, but anything that we do in a vacuum is irrelevant. We need to change the way we behave and do it and show people that it's fine. Not everyone will be happy with some of the changes that we need to do. There will be adaptations that will be needed for the new way that we're going to have to live. But what's really interesting is that a lot of the solutions to climate change actually put more money in the consumer's pocket, which is part of the reason why there's such resistance from both the energy generating companies and also the transmission companies. And I'll get into that a little bit. So some of the things that we could do when we conserve energy, the same way we did in the 70s, right? Turn off your lights when you leave the room. Actually, the fewer, when you drive less or when you use less energy, that saves money. And don't think by going paperless, you're saving a lot of energy, simply because data centers use a ton of energy. 2% of the energy used in the country is used because of data centers. So that's not always better either. Being more energy efficient in the cars that you drive, being more sustainable in how energy is produced. More than 50% of the new energy facilities that are going online are green energy. If you just replace coal with natural gas, as long as the natural gas doesn't escape, that's part of the problem, is we put them in these pipelines and we do all these other things, and methane escapes from these things, which is, again, a very strong greenhouse gas. Nuclear power. Nuclear power has its issues, but it does not produce greenhouse gases. It does in the process of building the nuclear power plant, and nuclear power plants are very expensive, and there's a lot of things that go along with it because we want to make sure that it's safe. But it's better than coal. Stop cutting down forests. Forests absorb carbon dioxide. Be smarter about the way we produce our food. There are many things that we can do which are both beneficial to the farmers and beneficial to reducing carbon. So greenhouse gas emissions, if we continue with, I don't know, doing everything as we normally do, we're looking at upwards of a 5 degrees Celsius increase, which would be catastrophic by the end of the century. Current policies don't get us there either. So the current policies that we have, we're looking at maybe a 3 degrees Celsius increase in temperature. Also not great. The pledges of the Paris Climate Accords and subsequent agreements still don't get us to where we need to be. We're missing the time where we could reach that 1.5 degrees Celsius, which is still going to mean significant impacts, but not the impacts that we would see if we continued with business as usual. So we have a lot of work to do. The Inflation Reduction Act really addressed how the consumer could participate in this whole change of energy sources by allowing for tax credits on how you have energy in your house, what type of vehicle you drive. But it also extends to businesses and energy efficiency and electrification and many other things. Here at UMass Lowell, we're changing some of the gas lines to geothermal. And so you'll have a geothermal heat pump or ground source heat pump that is provided in areas in Lowell where the space that was once occupied by a gas line is now occupied by that geothermal fluid. And so these are solutions that we have, but they're not free. And that does mean that we're going to see some cost passed on to the consumer. However, there will also be some savings. When we change from producing fossil fuels or only using fossil fuels for energy, the air will be much cleaner. Polluted air leads to heart disease, lung disease, asthma, and many other issues. The process of taking petroleum and turning it into useful fuel is so devastating for the environment. And ask anybody along Cancer Alley in Louisiana. It's not to say that green energy is perfect. It's not to say that my electric car is perfect, because there are trade-offs for everything. My electric car uses a lithium battery. The lithium battery, to create that, created carbon dioxide. Solar panels, you have to make them, right? But the difference, and one of the reasons why you can imagine that there's some pushback, is that when you establish green energy, whether that's a wind turbine or solar farm or what have you, there's the initial cost of having to establish this. And then it runs by the sun. The sun is what creates wind. And of course, the sun impacts those photovoltaic cells that are a solar farm. When you have a coal burning plant or a natural gas burning plant, when you make that plant, you build it, your expenses aren't over, because you have to continually buy coal, continually buy that natural gas, always have to use it. You always have to buy more. So if your business is selling coal, the last thing you want to happen is to change the way we produce our energy. And the powers that be have a lot of influence on policy because they stand to lose. And therefore, they will do everything they can to block this policy, which is all the more reason why it's kind of amazing that this got passed at all. Because to take any steps on climate change means that there's a very small population of very wealthy people that will be impacted. This is an example of adaptation, which is at the Thames in outside London. This is what happens if you have, say, storm surges or exceptionally high tides. they turn in on each other and block the rise of water. This is very similar to something we have in Lowell, which is called the Great Gates, which protects the canals that run through the city from rising waters. It's kind of an interesting comparison. This is in Thailand, where we're actually looking at wind turbines that are set up there for green energy. And of course, we could go on and on about green energy opportunities with agriculture. It's kind of a biggie. It's one of my favorite subjects, is how we can produce our food differently and actually reduce carbon dioxide levels at the same time. So researchers calculated that 20% of the world's per capita beef consumption is replaced with a meat substitute. I mean, that could be just vegetables. Like you do a little bit of pasta primavera instead of bouillon, whatever those meat sauces are. So it could reduce methane emissions by 11%. And deforestation associated with emissions by 50% by 2050, because a lot of the cattle feeding areas are regions that were once forested, and they deforested that area so they can grow food for cattle. That will equal more than 80% reduction in deforestation and carbon emissions. Further, if we replace 80% of the beef, we eliminate about 90% of forest loss. Tells you a lot about why we're cutting down trees. It's not to build new things. It's to make more agriculture land for cows. Right now, 70% of the agriculture that are the land used for agriculture in the United States is used to grow food for cattle and other livestock, instead of growing food directly for people. It's a very inefficient way to make food. However, there are other things you can do. One of the things we can do is, instead of fertilizing our fields with or putting certain minerals down, if you have soil here in New England, it tends to be somewhat acidic. So you usually like to add things like lime to your soil to change the pH. If you instead use a very common volcanic rock called basalt, that basalt ground up in your fields actually raises the pH as you want it to, making it less acidic, but it also adds nutrients and allows those fields to be more healthy. So you have more growth, and in the process, you also draw down carbon dioxide, because as that basalt weathers, it pulls carbon dioxide from the atmosphere, brings that carbon dioxide and carbonates to the ocean, and it changes basically into shells. So it's pretty handy. Definitely something that is being researched right now. In fact, we have a researcher here at UMass Lowell named Michael Ross, who is working on one of these things right now. All right, so carbon farming, we could sequester 4 to 5 gigatons of CO2. Current emissions right now are 41 gigatons, so this is really only addressing a small percentage. We need to really hit a lot more. Then that means that we need to do other things besides just change the way we farm. And I think this is one of the things that's very important to recognize, is that there are a lot of things we can do, but we don't know where to start. And sometimes it's just figuring out where to start. So this is in Tanzania, where they've dug out, this is an area that's no longer productive. They're suffering from what we call desertification, which just means you have soil that's no longer viable. So these little structures actually are really beneficial for blocking wind and allowing for moisture to accumulate in these little dug out half-moon shapes. And so over time, they start accumulating vegetation. And if they're, it's fairly easy to maintain. You've made these shapes, they take in the water. Once the trees start growing, it starts to block a lot of the wind, and you end up with, over time, a much healthier environment. So these 3 pictures are taken over a 5-year period, and you can start to see how this region is becoming better. It's recovering from desertification, and it's creating this green area that, of course, is much more beneficial as far as reducing carbon dioxide. So this is in Africa. If we could do this all over the place, that would be wonderful, right? That's one way we could start to draw down. And if also you make some of these trees, if they happen to be local trees, maybe they're food producing trees, that would also be useful. There's other things we can do to draw down CO2. They actually have a vodka that's made from air. Apparently this is an amazing vodka. It's a very crisp vodka. It's made from carbon dioxide and water. It's put together, and it's also $75 per bottle, so it better be good. But this is a product that is made from sequestered carbon dioxide. I always like to ask people if they recycle, and most everybody says, oh yeah, we recycle. But when I ask if you buy recycled products, usually I get crickets. Recycling is nice, it makes you feel good, but if you don't buy the products that are made from recycled material, what you're doing is nothing. Because that is all about supply and demand. If there's no demand and the supply builds up, then there's no need for it. So this is an example of taking something, we're asking, let's sequester that CO2. But what are you going to make from it, right? What can you do with it? And there are actually a lot of things that can be done with it. There's CO2 that's used in it's inserted into concrete to make the concrete stronger. There's CO2 where you can actually use that for a variety of different things. And this same company also makes jet fuel. Hopefully they don't get it confused with the vodka, but they make a sustainable jet fuel by using water and sequestered CO2. All of these things that we could be doing. Another thing that people ask about is, why don't we do geoengineering? They have all these things. Can't we just sequester carbon? And why can't we put mirrors in space? Put sulfur aerosols in the stratosphere. Well, there's a lot of reasons why we can't. There are some things that we could be doing. The idea of putting what we call solar radiation modification, which is putting those airplanes out in the stratosphere and putting in sulfur aerosols. Well, sulfur, when it combines with water, creates sulfuric acid, and that's not good. And the other problem is if we continue business as usual, but we have the solar radiation modification so that the sun reflects back and it doesn't get quite as warm. If that shuts down for a second, we would have massive accelerated CO2, massive accelerated greenhouse gas effect. And it also doesn't impact ocean acidification, which of course is another problem that comes from having too much CO2 in the atmosphere. Artificial trees or carbon sequestration usually takes a lot of energy to do that, which of course sort of defeats the purpose. But the other problem is that we need to scale them up. Right now, we have the ability to maybe sequester like 0.1% of the carbon dioxide. We really need to scale it up so that we could really kind of sequester quite a bit. And we need to make sure that we're putting it in a reservoir that's stable, that's not going to, release that carbon dioxide all at once. Changing the way that we produce our food is one thing that we could definitely do, and that would be really helpful. Something as simple as painting your rooftops white, as crazy as that sound, actually has a benefit. So these are things that maybe could buy us time, but it's only if we actually are acting on changing, mitigating, and cutting our addiction to fossil fuels. So Project Drawdown. So this gives us some solutions. The way we refrigerate should be changed. Wind turbines, increase them. Decrease food waste. Increase the amount of plants you eat. Protect our tropical forest. Educate women and girls. That's one of the biggest impacts that you can have, both on your economy. It definitely improves your economy, but it also reduces the number of people that are born. People who are well educated tend to have fewer children. So if you go through school and you start having children later, you have fewer children. If you are married at 15, you tend to have a lot of kids and a very unhappy life. I'm sorry for any of you who are married at 15. There are many things we could actually be doing. You don't have to do them all, but we do have to address this. If it is impossible for you to change the way you drive, is it necessary for you to fly everywhere? If it is impossible for you to change your diet, are there other things that you could be doing? Like maybe not wasting so much food. These are things to really consider. All right, action that must be taken now. Increase low carbon farming practices. Increase annual tree planting. Use 10% of farmland for agroforestry, which just means reducing, using that land simply to sequester CO2. Restore peatland and wetlands. Increase the use of land for energy crops. Not a big fan of that one. Depends on what it is. Don't be led astray by the idea of biofuels. If you're using a tree and you're cutting down that tree and you're burning that tree, you're burning the tree a lot faster than that tree could grow. So just because it once sequestered CO2 and you're going to grow another one, it's not the same. It's not an equal exchange. So biofuels are something to be very concerned about. Behavior change, reduce food waste, reduce beef, lamb, and dairy. It doesn't say completely eliminate it. It just says reduce it. If everybody did, it'd be amazing, but it's not going to happen. So just do what you can, okay? Going back to the idea of other solutions, offshore wind, dietary shifts, right? International shipping, just changing, being very mindful about what you do and where you buy your things. Do you really need blueberries that were grown in Chile? Shop local. Buying those blueberries that were grown in Chile, the amount of CO2 that was needed or produced by shipping those blueberries from Chile to Massachusetts is enormous. How much do you really need those? Start asking yourself those questions. If you can buy more locally, do. Carbon sequestration, again, there's a lot of work that needs to be done here. There's a lot that can be done in order to scale it up. But this only works if we stop our addiction. If it's just a way to delay, that doesn't help us. We need to act and to change direction now. We can't use this as a delay tactic. Remember that the richest 10% in the world are responsible for 50% of the carbon emissions. The poorest 50% are only responsible for 10% of total emissions. So wrap your head around that one a little bit, okay? So who needs to make changes in the world? Is it the poor people? They're the ones that are most greatly impacted by climate change. But it's the richest people that need to really start thinking about how they're going to change and what they're going to do, because it's their children and their children's children and themselves that are going to be greatly impacted by this. And then the last thing you can do, and the most impactful thing you can do, because this is such a big issue and an urgency I can't understate, is vote for whoever will act on climate change. This is bigger than we are. This is something that needs to be addressed at the policy level. You vote for who will act on climate change. You tell others to vote for people who will act on climate change. You yell from the mountaintops, vote for whoever will act on climate change, because otherwise we will never address it. Nope, back to the beginning. All right, so that's I'm going to stop sharing. That's my incredibly long presentation. Look at it, it's nighttime now. I've been talking so long. So I'm hoping that if you have any questions, I'll be able to answer them. I'm going to a presentation for an economist to talk about climate change and climate change economics sometime later this month. And maybe if I learn something from that, I'll be able to send it to you guys for this as well. So it has been a pleasure. I always like working with LIRA. usually getting lost in the woods. But this is a really important subject, and I appreciate you if you got all the way through this recording. Appreciate you listening to this. Have an amazing day, and I hope to see you all soon. Thank you.